The main topic that will be discussed within this PowerPoint is exercise in the heat and cold and how different environments affect the body in PE lessons and sport. Here are some keywords that help with the understanding of the topic being discussed. Firstly, homeostasis is the term used when describing the body's tendency to maintain a steady state despite external changes. The hypothalamus is part of the central nervous system and forms a region of the forebrain which controls body temperature and other homeostatic systems. Now, there are two control systems for temperature regulation in endotherms. The behavioural system involves conscious voluntary acts to adjust physical characteristics in an alternative environment. An example of this would be moving out of the hot sun and into the shade, or putting on a sweater to keep warm. The physiological system consists of involuntary responses of the body that generate or dissipate heat. As we can see, these two responses are highly important in ensuring the body does not under or overheat. If the performer's core internal temperature wavers just a few degrees above or below a homeostatic state, 37 degrees Celsius, then physiological side effects can occur, such as heat stroke or hypothermia, and in the end, even death. Evidently, the idea of how easily the body's temperature can fluctuate and produce negative side effects of performance highlights the importance of physiological thermoregulatory responses. Therefore, one of the key systems that ensures physiological strain does not impact performance is the cardiovascular system. There are several different bodily adaptations that occur within this system, one of the most basic being an alteration in a performer's heart rate. Arguably the most crucial function of the heart is its ability to increase the number of beats it performs per minute in order to accelerate the delivery of oxygen to the working muscles. More importantly, this process occurs when the performer undergoes exercise in any environment, hot or cold. The cardiovascular system has two processes which aid the distribution of blood flow: vasodilation, the widening of blood vessels, and vasoconstriction, the narrowing of blood vessels, work together whilst the body is exercising as oxygen is needed in the correct working areas of the body. Vasodilation will occur around the performing muscles to support them working through increased blood flow, whereas vasoconstriction will occur in the arterioles supplying non-essential organs such as the intestines and liver. Blood flow during and not during exercise is a crucial bodily function for the below reasons. Not only do the two processes preserve bodily energy, but they direct more blood from and, more importantly, back to the heart, as it is a muscle and requires extra oxygen during exercise. So, how does the body circulate blood around the body? The process is summarised here, and whilst this occurs, oxygen and carbon dioxide are broken down into different elements within the blood flow, as stated in this slide. Once these cardiovascular functions have redirected blood flow, the body can react to the surrounding environment and undergo the sufficient bodily functions. If the temperature is too hot, blood vessels will vasodilate and the body's eccrine glands will begin to produce sweat. Water makes up approximately 60% of your total body composition, so it is the essential nutrient for survival. As sweat evaporates from our skin, our core internal temperature is lowered, allowing the body to maintain as close to a homeostatic state as possible. However, there are several defects that occur within the body when a performer first begins to train in the heat, and these can be seen in the top left-hand side of the screen. Once the performer begins to regularly train and perform in warm environments and temperatures, it becomes what is known as acclimated. The shown quote reinforces how, in general, heat acclimation is a long-term benefit of training in extreme environments, and below are some of the physiological benefits of heat acclimation. This case study reinforces how not only are you fitter if you sweat more, but it suggests that training in higher temperatures is more beneficial for the body and performance than training in cold temperatures. Looking at the case study, there are two performers, one being a trained long-distance athlete and the other an individual with no training experience in exercise. The experiment aimed to figure out whether internal temperature over 4 hours increased adjacent to sweat rate per 4 hours. The results showed that although both performers' sweat rates increased, the rate at which they did differed. Consequently, this reinforces how, due to the athlete's eccrine glands releasing sweat earlier than the non-athletes, this ensures that the athlete's homeostatic state is maintained for longer and thus allows for the body to maintain performing maximally. The second case study, completed by Musa in 1988, highlights further benefits of heat acclimation and in general training in the heat. For example, by the end of the 90 minutes, cardiac output was similar for both sets of results, but the post-acclimated athlete's cardiac output consistently increased throughout the 90 minutes exposure to cold air. This suggests that acclimation training can be used in cold environments as well as heated environments. However, highlights how heated environments may be better to train in when aiming to improve performance due to the consistent increase in cardiac output from the post-acclimated performer. In general, these findings suggest that acclimation training in the cold can prove to be just as effective as heat acclimation training. However, it simply depends on what sport the performer wishes to improve their performance in. Same cardiovascular processes of vasoconstriction and vasodilation occur when the body is exercising in the cold, as oxygen still needs to be redirected and delivered to the working muscles. This time, the core internal temperature is too low, and therefore the process of shivering occurs. This involves rapid, repeated skeletal muscular contractions, leading to heat production through the inefficiency of ATP utilization. Located in the posterior hypothalamus, there is an area called the primary motor center for shivering. It becomes excited by cold signals from the skin and spinal cord. Therefore, this center becomes activated when the body temperature falls even a fraction of a degree below its homeostatic state. Thus, the skeletal muscles begin to frequently contract and relax to generate heat. With increased amounts of shivering comes an increased expenditure of energy in order to allow this process to occur. As a result, it can be argued that although shivering is used as a calorie burner, exercise in the cold may not be as beneficial as exercise in the heat due to how much energy is needed to generate a shiver. Further reasons to suggest why exercise in the cold may or may not be as beneficial as exercising in the heat can be seen here. An interesting study taken from Cell Metabolism in 2014 highlights how shivering is now being examined as a potential weight loss therapy. Shivering, like exercise, activates the hormone irisin. Irisin prompts brown fat cells to use energy to produce additional heat, which burns extra calories. However, cold extremities require the cardiovascular system to work harder, as the heart must work more to pump blood around the body. Although in the long term might help to benefit and keep the myocardium strong and the heart generally healthy, in the short term it can put the performer's health at risk. It could be argued that depending on what an individual would like to gain from the training that they are doing, then both hot and cold environments can provide short and long-term benefits to the body's cardiovascular system. However, if the main focus is on pupils taking part in regular PE lessons, then the type of sport they are doing will dictate what environment the PE teacher wishes their pupils to perform in. In order for the body to ensure it maintains its homeostatic state, further physiological functions take place. The shown equation highlights how this can be done. Taking these processes out of the equation and looking at them individually, we can see that there are four main processes that can help the body to maintain homeostasis. Heat can be lost through conduction, convection, radiation, and evaporation. So, just how beneficial is it to a performer if they train in the heat? Certain outcomes of heat acclimation have been proved to rival those of altitude training approaches and lead to improved performance across a range of temperatures. Although heat acclimation exposure provides considerable ergogenic benefits in cool conditions, the benefits can arguably only truly be seen when a performer undergoes aerobic training in cool conditions. As a result of this, it can be argued that a mixture of hot and cold training would benefit both an elite athlete and a pupil in a PE lesson. This is because the necessity to utilise both environments in order to observe the physiological benefits. The drawbacks that training and performing in the heat can have on the body emphasise the importance of behavioural thermoregulatory responses. Whether it's a PE teacher ensuring that their class takes water out with them and has regular breaks out of direct sunlight, or an athlete acclimatising abroad and choosing to train during the latter part of the day, Sorka 2012 summarises the importance of these responses. Here are some of the examples of behavioural thermoregulatory responses in the heat. Most importantly, the elephant experiment. It has been proposed that elephants consistently exposed to warm environments learn to store heat, becoming heterothermic and conserving body water. This can be applied same to humans, and therefore it might be argued that thermoregulatory responses in the heat are more beneficial. One example of a behavioural thermoregulatory response in the cold is layering. Thick clothing will ensure that not just the body is vasoconstricting, but the layering acts as a secondary non-layer to insulate heat, in which the body may lose. In general, looking at the benefits and drawbacks that hot and cold environments can bring to a performer's training, both are beneficial, and when deciding which one is better can simply depend on the level of the performer, either a PE student or athlete, and what benefits they want from the training.